Let's look at some of the many ways you can do a material and energy balance on a chemical reactor. We use the example reaction of ammonia reacting with oxygen to form nitric oxide and water. These will all be in the gas phase. Now this reaction is not balanced, so we'll have four molecules of ammonia, 5 of oxygen, 4 of NO, and 6 of water. Before we continue, let's give these molecule symbols. I'll call ammonia A, oxygen B, nitric oxide C, and water D, just for shorthand. Now the heat of reaction is given at standard conditions, 25 degrees C, that's what the little superscript 0 means. This is minus 904.7 kilojoules per mole. So this many kilojoules per mole of 4 molecules of ammonia, 4 moles of ammonia, or 5 moles of oxygen reacting, or 4 moles of nitric oxide and 6 moles of water being produced. Now the problem will be that we have a chemical reactor and we're feeding some material to it and bringing out a product. The feed will be 40 moles of ammonia, 40 moles of oxygen, and note that is not a stoichiometric proportion. And just to make life more difficult or more interesting, we'll have 40 moles of water going into this, in with this feed, and it will be liquid water because the temperature here of the feed is only 75 degrees C. Now, we don't know how much is coming out, so we'll symbolize any unreacted A and B as Na and Nb moles of A and B, and product Nc and Nd, the nitric oxide and water. These will all be in the gas phase. It's gas phase unless otherwise indicated. And the temperature here will be 300 degrees C. The question will be how much of each material comes out and how much energy must be removed from the reactor to assure these conditions. We need one process specification, and that will be that the fractional conversion of A is equal to 0.5. 50% of the ammonia fed to the reactor will be reacted. We'll do a degree of freedom analysis around the reactor. The unknowns are Na, Nb, Nc, Nd, Q, and if we use extensive reaction, we'll have that as an unknown, the extent of reaction. The equations that we have available are 4 mole balances, one for each of our chemicals, A, B, C, and D. We have one process specification, that is the fractional conversion of A, and we have one energy balance. Now, if we can, we'll do the material balances first and then do the energy balance. In this particular case, we're given the outlet conditions and we need to calculate Q. So this is an instance where we can do the material balances first. So we will leave the energy balance for later and leave Q for later. So we actually have 5 unknowns to solve for right now and 5 equations. So those 5 equations are the mole balances for A, B, C, and D, and we also have our fractional conversion. So we need to write these equations and solve them. So the mole balance for A, using extensive reaction, is the amount coming out is equal to the amount fed, which was 40 moles, minus the extended reaction times its stoichiometric coefficient, which was 4. So 4 times the extent of reaction. It's a reactant, so the stoichiometric coefficient is negative. For B, we have N sub B is equal to 40, that's the amount fed, minus 5 times the extent. For NC, we're not feeding it, so the feed is 0. We could leave that off if we want. Plus, since it's a product, 4 times epsilon. And for D, we are feeding some. It's 20 moles. It doesn't matter what phase it is at this point. And this is produced as 6 times epsilon. For the fractional conversion, we have the amount fed of A minus the amount coming out over the amount fed is equal to 0.5. Now this equation, this last one, only has one unknown, so we can calculate that Na is equal to 20. Now that we know Na, we can come up here to the first equation and see that if Na is 20, then epsilon is equal to 5. And so Nb is equal to 5 times 5 is 25, from 40 is 15. N sub C will be 4 times 5, or 20. And N sub D will be 6 times 5, or 30, plus 20 is 50. And that concludes the material balance, the mole balance. In the next series of tutorials, we'll do the energy balance, determine how much heat needs to be removed from the reactor, using one, the heat of reaction at 25 degrees C, so that our reference state has to be the same, 25 degrees C, and gas. We also will calculate the heat of reaction at 25 degrees C. We'll calculate this using heats of formation. Third, we'll determine what is the heat of reaction at a different condition, and we can choose, for convenience, either the inlet or outlet, but I'll choose 300 degrees C, and that'll be my reference state. I choose that because the products are all gas, just the way I wrote the reaction. So 300 degrees C and gas. And finally, 4 will use the heats of formation. And our reference state will be 25 degrees C and the elements as found in nature. This is all coming up in future tutorials. Next to the link, next to these links to the tutorials, you'll see a link to a spreadsheet. I believe it'll be called Energy Balances with Reaction Tutorial. It's a Excel spreadsheet. I encourage you to open that spreadsheet and follow along with the calculations of Q using these 4 different methods.